So we'll finish up Module 6 on refrigeration and liquefaction by first looking at actual cycles and how they are different from this ideal cycle, and then also looking at different ways that we can build refrigeration cycles. So the device that's the most troubling in a refrigeration system like this is the compressor. Okay? The reason the compressor is a problem is, first of all, if it's not reversible, it's going to cost us even more to operate that refrigerator. So that's a problem. It also is the one with the moving parts. It is the only piece of equipment with moving parts. So it is the most likely to break down. So we usually really scrutinize the compressor very carefully. Now, remember, compressors require work input. So the process efficiency for a compressor is the ratio of the ideal to the actual, because the actual will be more than the ideal amount of work. These are both work required, so depending on your sign convention, these would both be negative, but in absolute value sense, there's going to be a larger quantity of actual work required. Now, for a pump is the same as for a compressor. It's H1 minus H2 ideal for the ideal work and H1 minus H2 actual for the actual work. So pumps and compressors, the formulas remain the same. What will change is simply that I'm looking for gas properties instead of liquid properties. So, if we go back to that same original problem we had, but change my compressor to an 85% efficient compressor. Now, what we had found before was that we had, it's this first column of work here, okay, that we had done this and we had approximately a coefficient of performance of 5 for refrigeration mode. What I'm going to do for the actual cycle is take this compressor work, and ideally it was 26.4 kilojoules per kilogram. 0.85 is equal to the ideal work over the actual work. So therefore the actual is the ideal divided by 0.85. So the actual amount of work required is negative 31.1 kilojoules per kilogram. I can use that to calculate the enthalpy at the exit. And if I have that, then I can recalculate the amount of heat transfer. Now notice it does not change the cooling load, the Q sub L, at the low temperature. It does change the load at the high temperature. And it does, as expected, lower the coefficient of performance. So in this case, with an 85% efficient compressor, my efficiency measured by coefficient of performance dropped from a 5 to just above a 4. So that's a fairly significant drop, but not unexpected. Now the next thing I want to do is talk briefly about other ways we can put cycles together. I mean, the options are fairly limitless. A lot of times what we're going to do is we're going to combine things where we put power cycles and refrigeration cycles together so that our power plant can drive the refrigeration. After all, we've got equipment there where we are going to be condensing our fluid in the power plant, and I can use that as heat input to my refrigeration. So there's various ways that we can do this, and I just snagged a couple of drawings from online. There are so many of these that you can find. And typically what they have is that they have a pairing at a heat exchanger someplace, here or here, or where the heat exchangers have heat out of one device and into the other cycle. Cascade refrigeration is another really important thing to consider. And what a cascade refrigeration system is able to do is take a refrigeration need. Maybe the low and high temperature extremes are just too great for any one working fluid. So what I can do is I can use one working fluid as low as I can get it, and then switch to a different, maybe more expensive working fluid to complete the refrigeration cycle. And again, what you'll notice is that the pairing always happens at a heat exchanger. So the heat out from one goes into another. And this is like I say, a great way to be able to achieve really extreme temperature differences when one fluid is just simply not going to work. And you know everything there is needed to analyze something like this because it's just two different refrigeration systems coupled with an equation that says, the heat out here is equal to the heat in here at the heat exchanger. Now the last little bit we want to look at is the Linde liquefaction process. This has been a very important process for engineering. It's a way that we can do things like make liquid nitrogen. Surely you have played with liquid nitrogen at some point in time. If you want to get liquids from air, the Linde liquefaction process is the most common way of doing it. It really is almost the same as our regular vapor compression refrigeration cycle, with one major difference. The fluid that I'm sending through inside the tubes is going to become my product. So when it goes through that Joule-Thomson valve, that expansion valve, it's going to have liquid in there. If I drop the liquid out into some sort of collection tank, okay, and then let the gas go on through the cycle, then I can just run this, pretty much forever, except that I'm going to keep dropping liquid out, and I'm going to run out of fluid. So we have to add a makeup gas. So really, the difference is that the amount of liquid that is formed at this step here, I'm going to remove, and I'm going to replace it with an equal quantity or mass of makeup gas just before it enters the compressor.